In this lecture in Climate and Earth 401, I'm going to talk about the tangential coordinate system. The tangential coordinate system, which is a coordinate system sitting on the surface of the Earth, is a coordinate system that we will use most frequently in the course. It's been mentioned in several of the lectures, and it has been also introduced in the material on mathematical knowledge required for the course. The purpose of this lecture is simply to extract that information on the tangential coordinate system and to perhaps clarify some aspects of the coordinate system that frequently cause confusion as we're thinking about rendering the equations of motions and analyzing observations. If we have here a sphere, and this is representative of the Earth, then the idea of a tangential coordinate system is that at any point on the surface, we will form a coordinate system that is local to us, to our point of view. One part of that coordinate system will have a horizontal plane that really only officially touches the surface of the Earth at one point, the tangent. This just represents the plane in one horizontal direction. The other horizontal direction is into or out of the slide, and this is the local vertical here. You'll see a couple aspects of this coordinate system. One, if you stay very close to where you are, you can imagine that it is a plane. But if you go far away, then the Earth starts to curve away from you. So if you're in this coordinate system and looking far away, then you do need to consider the curvature of the Earth. The other thing, by looking at a second tangential coordinate system for another person, perhaps over here, is that you'll see the vertical changes. It's the local vertical. Local vertical points down towards the center of the Earth, so gravity is aligned along the local vertical. In a rotating coordinate system, which we will consider, the rotation around the local vertical is what is important for apparent forces such as the Coriolis force. So in the tangential coordinate system, we place the coordinate system here on the surface of the Earth. I have attempted here to express it in 3 dimensions, where this is the south to north direction, this is the vertical direction, and this is the east to west direction. We take the coordinate system to be positive in the x direction going from west to east, positive in the y direction going from south to north, and positive in the z direction going from the surface to above. Here we are explicitly representing the rotation of the Earth, and the rotation is from west to east. Our coordinate system is therefore a tangential Cartesian coordinate system on the surface of a spherical Earth which is rotating. And if you consider all of those things together, it is really pretty complicated and requires a lot of accounting in order to express vectors and the equations of motion correctly. Here's another view of it. This is a view that you might consider to be a 2-dimensional view looking at a ring of the Earth. In this case, the tangential coordinate system is drawn such that here's the west to east direction, here's south to north, and then here is the local vertical. U, the velocity vector, is written such that U is in the I direction, V is in the J direction, and W is in the vertical. A couple other important definitions to go with the tangential coordinate system. Our body force gravity, which points along the radius to the center of the Earth, sometimes will be represented as a vector along that radius, which will be r over the magnitude of r, which is a unit vector in the radial direction from the center of the Earth. And this vector also aligns with the local vertical and the unit vector k. Another important direction to consider is the axis of rotation, which is different depending upon which latitude you're at, and the direction that is outward from the axis of rotation, which is the direction that, say, the centrifugal acceleration or the centrifugal force acts in, is another important direction, and this force then needs to be rendered into the tangential coordinate system in the local vertical. Considering the local vertical and the rotational aspects of this, it is the rotation around the local vertical which is the apparent force called the Coriolis force. The Coriolis force is weakest at the equator and it's strongest at the pole. Just for some definitions, in this figure we have the latitude represented here as the angular measure of where we are away from the equator. This distance r, which is the radius around the rotational axis, is going to be equal to a cosine of the latitude. And with that, I've introduced the tangential coordinate system and a number of important attributes of that coordinate system which need to be considered quite carefully in the development of the momentum equations.